Is it fine to see you?
Yeah, you can see your PPT. Yeah.
Okay, thank you very much. Still, good morning, everybody. I would like to present my work on intrinsic mechanism of thrust production of a pitching hydrofoil. Not only one hydrocoating, there will be maybe more than one, like two. And if you particularly see that the baby is oscillating in the staller, and in the bottom video file that there's a foil, foil-like fish-like foil is oscillating, and we have generated vortices in the wake, that is the reverse Kalman vortex. We'll mainly focus on when this foil oscillate, what is the mechanism of thrust production. So, it is not full screen. Now it is full screen. Yeah, sorry. Thank you. Then here is the presentation outline. I will give some background. Then I did some experiments on thrust measurements, live fish experiment. Then results on numerical simulation, single foil, two foils, and finally some conclusion. Here you see there's now it's the age of robots around the world. Everywhere you will find different kind of robots. So also not only on the earth, also in the ocean. There, every country, every groups try to explore the undersea. Then they need robots to work. And also in nature, you will find like animals, they live in a group, not they are isolated. There are many different reasons why they live in a group. Particularly, we'll explain here in terms of aerodynamics or hydrodynamics. Why do like a fish, the most known ocean animals? That's one is the social. That's like a human. For like a decision making, information sharing, and also in the aspect of biological, mating, hunting, foraging, and also for the survival purpose, like to confuse the visual signals and also predator surveillance, and in terms of hydrodynamic saving energy. So our aim is to understand the schooling behavior of fish from the perspective of fluid dynamics or hydrodynamics, where the flow around like two swimmers involves the most generic flow features for real fish schooling. Thrust is the most important factor, like for a prey-predator competition. So the hydrodynamic origin of thrust generation must be understood completely to explain how a quick start is possible to escape from a predator. Definitely for quick start, the fish need a high thrust, even higher than the predator. And how to get backward movement. Sometimes predator comes from the front, then the prey needs to go back quickly or have a quick backward movement. Then how they can do? What is the physics? If you go some previous experiments by other researchers like Goody and Diana, they made experiments of the oscillating foil, and they found reverse Kalman vortex corresponds to the thrust generation, and the like a Kalman vortex corresponds to the drag. And Bill et al. Did experiments of a dead fish behind a D-shaped cylinder. So the D-shaped cylinder make a wake behind it, and if a dead fish is put in the wake, then the fish can easily go upstream. That means if a dead fish follows a live fish, that the dead fish can easily follow the live fish. That means can move forward, have a thrust. So Guriodin make an experiments changing the STD and A-star. STD is the we call the Stahel number, that is a function of frequency of oscillation, and the D is the thickness of the foil, and U infinity is the flow velocity here. So this is the function of like a Stahel number. The Stahel number STD is a function of frequency and D, and also the U infinity, the flow velocity or the swimming velocity. Here, A is the amplitude of the oscillation, the foil oscillation. The vertical amplitude is A. So we call A star is A over D. That's the normalized by D. So here, when we change the S, there are two governing independent parameters. Okay, one is the STD and another is the amplitude. This is the force oscillation of the foil. Okay, manually. So when we change the STD and the amplitude, okay, STD and the amplitude, they found a different kind of flow patterns. Like one is the Karman vortex wake, second is the 2S aligned wake. We'll explain later these four flow patterns. And RKV is the reverse Karman vortex. And this one is the deflected reverse Karman vortex. That means it is not the axis symmetry, but deflects in downward or upward. And their position are shown here. Like at small STD and small amplitude KV wake, Karman wake forms. When we increase the STD or A star, then 2S aligned wake forms. If we increase further the STD or A star, then we reverse Karman's vortex will form. Okay. Further increase in STD or A star will give you the deflected wake. This is the boundary between thrust and drag. Okay, that means this is the thrust region, this is the drag region. And here we'll explain the different flow patterns in terms of flow structure. This is the KV wave, where you see the positive vortices appears in the lower side and negative vortices on the upper side. And in the 2S aligned wake, the both positive and negative vortices appears on the symmetric line. And for reverse Karman vortex, the phenomena is opposite to the KV wake. Okay, it's opposite. Now the positive vortices appear on the upper side and negative vortices on the lower side. And this is the deflected wake. That's the wake is not symmetry. It's like here following the lower side, moving deflected to the lower side. But all upper three wakes are symmetric about the y equals 0 symmetric line. Let's see the experiments on live fish. To do the experiment of live fish, we made a setup for holding the fish. Here we have a straight bar. Here is the pin joint or hinge joint that can move like this. And we put a load cell here to measure the thrust. To hold the fish is very tricky and really difficult. So we make two frames, one in the upper side and one in the lower side, to hold the fish, okay, tightly. And we have the water tank here. We put water in the tank. Then this is the vertical frame. Is this one? This setup. And to make a clear picture, we use some mirrors and also the camera. Let's see the different techniques for holding the fish. This is the bottom part of the holding device, like this one. Okay, this one here you can see. Here we have the upper part and the lower part. So if we put this fish between this hard, this is made of steel, definitely the fish may get hard. So we put a sponge, okay, between the two frames, okay, like this. When like here you see that there's the two fish, there are two frames and fish between them. So to tight, we did not use a screw, rather we use the elastic cord so that fish can get a little relaxed instead of tight. So here are the different techniques. Finally, the second technique is that we remove the lower part. When we put the lower part, actually fish does not want to move. Like here. Finally, usually the fish try to escape suddenly. Rather, we want it will be swimming. So we try to cap the head of the fish using a mosquito net outside. When you cap the fish head, really it does not move at all. So then we use another techniques like a thread on the fins, pectoral fins. If we go to the next slide, then it will be more clear. Like this is the one case when the fish hold, it's trying to escape. What the fish do actually, just pay attention to the pectoral tail fins actually. Then you will see it's moving fast and making it like a C shape, trying to move backward. Then lose the setup, then trying to move forward. So there are two different physics for backward movement and the forward movement of fish. When we tightly hold the fish, actually it does not, somehow fish knows that he cannot escape. So in that case, it does not try to move. But when she understand, the fish understand that she can escape, it can escape, then he move rapidly. Using pectoral fin cords here, this is another video. In that case, there's very vibrant, fish very vibrant, always moving, trying to escape through and through. In one case here, we tried to measure the thrust. Thrust is really difficult to measure. And when it is trying to escape from the back, when it's from the back, then definitely thrust getting negative. And this is the two basic mechanism for the forward swimming and backward swimming. Okay, like backward movement and forward movement. For the forward movement, actually, there are the stroke around the symmetric line is different. The inward stroke is fast for the forward swimming, and the outward stroke is slow. This is opposite for the backward swimming. The inward stroke is slow for the backward, and the forward stroke, I mean the outward stroke is faster. So when it happens, the faster stroke, it can push backward fluid more rapidly, so the fish get forward thrust. And when it has a faster forward or the outward stroke, then really fluid is pulled forward, so the fish move backward. Then simulation on single foil, we did simulation for the single foil, changing the STD, this is the definition, STA, this almost the same definition, like D means based on D, A means STA means based on A, like then similarly STC. And A star is the amplitude ratio. The Reynolds number here was 200. This is the thrust coefficient definition calculated from the thrust force, and this is the power coefficient given to the fluid. This is the theta, the rotation angular displacement corresponding theta dot, and the acceleration. Here is the time history of CT means thrust and power CP. Like one interesting question is that when the thrust during the movement of the foil, when the thrust is maximum or when thrust is a minimum. Similarly, when we need more power or minimum power. So what is interesting here, this is the 0 means the equilibrium position, neutral position, and omega t, pi means like 180 degree, pi by 2 means 90 degree. That's the extreme position. So when it's moving from the neutral position, equilibrium position to the maximum amplitude, the CT is increasing. The maximum thrust happens just beyond the extreme, beyond the extreme, and minimum thrust occurs just somewhere before the neutral, after the neutral, okay, minimum position, after the equilibrium position. And is there any relationship between the CT and CP? Yes, there is. If you get the curvature of the CP, it is understood that when the curvature of CP variation is 0, then we have the maximum thrust. This is the relationship. If we put the information in the form of sketch, it is clear. You'll see here the maximum thrust happen after the equilibrium position. The minimum thrust happen after the equilibrium position. And before the equilibrium position, we have the maximum CP. Similarly, after the before the extreme, we have the minimum CP, and just after the extreme, we have the maximum CT. Just when the foil trying to move toward the neutral position, it has the maximum CT. This is the contour plots of CT, CP, when we change the STD and A state. Okay, here you will see the CP bar time in power. We need higher power when we increase the STD or A state. Similarly, CT also increases when we increase the STD or the A state. Okay, almost monotonically increasing. However, the efficiency is also increasing. Okay, this dashed line is the drag thrust boundary. Okay, this is the drag region and this is the thrust. This is the thrust region and this is the drag region. And then where is the optimum? How do I say that's the thrust or the acceleration? Where it's the maximum thrust against change in CP. If we get the dCT over dCP, that means change in thrust with respect to the power input. We found that when the STD is about 0.25, then we have a maximum gradient of CP. That means when a fish or a bird try to fly, this condition will be for like start of flying. Then we did some mathematical formulation to understand the physics behind it. So we consider the wedge-shaped body, like this is the foil, thin foil, and these are the fluids around it, wedge-shaped fluid. And this fluid actually, due to the rotation, they moves along the foil and also in the transverse direction. As such, we have three kinds of acceleration of this fluid. One is the Euler acceleration, centrifugal acceleration, and Coriolis acceleration. This Euler acceleration and this Coriolis acceleration are connected to the torque or power, and this centrifugal acceleration indeed is connected to the thrust. So here we consider the infinitesimal volume of the fluid, then we got the mass and also the moment of inertia of this fluid, and the corresponding acceleration of fluid is here, velocity and acceleration. Then torque we found from Euler and Coriolis acceleration following this equation. Okay, like this is the Euler acceleration torque, and this is the Coriolis acceleration torque. And if we integrate this one, we found this the final equation. Similarly, the thrust we obtained from the centrifugal acceleration as this one. The Fd0 is the drag force when it is not moving. The foil is not moving, so it must overcome. Thrust must overcome this one. Then there will be positive thrust. Then time mean thrust obtained this way, and in the coefficient form, finally we found the CT is function of ST cube. Okay, is STA cube. That means it varies with the power of S3. Okay, cubically varies with the STA. And in the power, the final equation, again, we found the CP is directly proportional to the STA cube. So STA, that means that includes actually the amplitude and also the frequency, is the more crucial parameter for the thrust and power. And efficiency, again, we found the efficiency varies inversely proportional to the ST cube. Okay, so if you have higher ST, then we have the lower efficiency, but higher thrust. So then our scaling factor gives quite a good matching with the literature results. This is our formulation, and we accumulated the results from the literature. We found good agreement. This relation obtained from the theoretical analysis, and similarly also the power, it follows a good agreement, and efficiency we also found the similar agreement inversely proportional to the STA. So our assumption and the formulation is very good, and also that gives that the understanding of the production of thrust and also the power. Then if we want to put two fish, like fish is cooling, then we use two fishes in side by side, and we oscillated the two fish in phase, phi equals 0, that means in the same direction like this, and also the anti-phase phi equals 90 degree, that means it is something like this, okay, at the same time. So we considered anti-phase and in-phase condition, and also we considered the tandem arrangement, one phase behind the other. Again, in that case, we two phases are considered, the phi equals 0 and phi equals 180 degree, again in phase and anti-phase. We'll see the results for the two side-by-side phases, okay, two side-by-side phase. Like one is the square symbol, anti-phase and in phase. What we see that when the two phase move in anti-phase condition, they have a higher thrust. That means for the in-phase condition, we have the lower thrust. So we can say if two fish move side by side, swim side by side, then their tail should oscillate in an anti-phase fashion. Okay, they're like this one. This is the anti-phase. This is the in-phase. If we see the power, still they need power, more power, but in final decision is the efficiency, and we see that for the efficiency for the anti-phase condition is higher than the in-phase condition. So that's the final conclusion, is that if the two fish swim side by side, they oscillate their tails in anti-phase fashion. Like this is the flow vorticity structure when the for the two condition, anti-phase condition and in-phase condition. You see here we have the stronger vortices, of course the Karman vortices, but here the weaker vortices. That means formation general of stronger vortices, stronger jet actually corresponds to higher thrust and also the higher efficiency. And then for two tandem foils, now both are in tandem, one behind another. In this case, the scenario is different. Now you see here, for the in-phase condition, we have the higher CP, also the higher CT. So if one fish follows another, then the two fish will oscillate their tails in anti-phase condition. Sorry, in-phase condition. In anti-phase condition, in phase condition, that means they move in the same direction together. So in that case, they need lower power but get higher thrust. here, this is the oscillating foil wake structure for the in-phase and anti-phase condition. Then if you consider the total performance for the two tandem foils, what we see? Again, we see the total power they need for in-phase is higher. Also, thrust is higher for the in-phase condition. But if we consider the efficiency, but the efficiency is lower for the in-phase condition. This scenario is different. If they need to escape from the predator, then they need actually higher thrust. Okay, but in terms of normal swing, they need higher efficiency. So for escaping or fast swimming, they need higher in-phase oscillation. But for high efficiency, like a relaxed swimming, they should have anti-phase condition. So I come to the conclusion. The first is the instantaneous thrust is maximum at the inflection point of power. Thrust is maximum near the extreme positions, and more power is required to move the hydrofoil from the extreme to the mean than the other way around. And pressure on the hydrofoil surface is dictated by the fluid inertia. And we found the three scaling factors that agrees oil with the data in the literature. For two side-by-side foils, antiphase oscillation enhances more thrust and power coefficient than the in-phase oscillation. For tandem foils, the scenario is opposite. Here you will see the structure. Thank you very much for your kind attention and patience.
Yeah. Do you have any question? Or do you consider the feedback control problem? For example, like the hand hold the fish, and then once the fish, moving, and then the hand also, flexibly control the fish.
No.